So it's Summer Conference of Tournaments of Towns 2020. Today is January 26 of 2021. So everything is on time. Our project is called Phase Spaces. And let's talk about the definition of the phase spaces. So phase space is a set of all possible states of some system. And it is easier to understand this definition using some examples. So we have plenty of examples in our project, but we'll start with problem number 0. It's a problem about porridge, as you may see in a list of problems. So we have a round table. It's view from the above. And we have 3 kids sitting around the table. And each of the kids has a plate of porridge. So, they do the following. Every minute, each kid takes a porridge from its plate, divides it in 2 equal parts, and puts these parts to the plates of its neighbors. And they do it simultaneously, so at the same time. The question is, can we prove that after several minutes, all porridge will be spread almost equally. And when I say almost equally, I mean that it will be spread equal up to 1%. So all the porridge will be spread equally up to 1%. And actually, there are different ways to solve this problem. And we will show you, I think, easier and the most beautiful way. And it looks like this. So suppose that the first kid, let's say that this is the first kid, and he or she has X amount of porridge. The second kid has Y amount of porridge, and the third kid has Z amount of porridge. So you can see that after 1 minute, the porridge would be spread the following way. So the first kid gets half of Y's porridge and half of Z's porridge, so it's Y plus Z divided by 2. The second kid gets X plus Z divided by 2. And the third kid gets X plus Y divided by 2, and so forth. So as you can see, I guess after several iterations, it becomes harder to see what exactly amount of porridge in the terms X, Y, and Z each kid has. So let's draw a picture. Well, suppose that we have a fixed amount of porridge, of course. So X plus Y plus Z equals some constant. And of course, each kid has greater or equal than 0 amount of porridge. So X, Y, and Z are all greater or equal than 0. And so by looking at this equation and these inequations, you probably can guess how the picture will look like. So I will have 3 axes. So it will be z, x, and y. And x plus y plus z equals some constant is a plane. Well, I'll try to draw it clearly, but I'm afraid I'm not a good artist. So yeah, we have some plane. And by these restrictions, we actually get a triangle. So we get a triangle with vertices. So let's see, this vertex is 0, 0, C. This vertex is, well, 0, C, 0. And this vertex is C, 0, 0. So we got 3 vertices with the following coordinates. And let's see, I'll draw this triangle in such a way that I look at it from this way. So it's actually a regular triangle. And well, if you look closely to this transformation, you might guess that this is actually a homothetic transformation. So the thing it does, well, let's look at this vertex, for example, it's 0, 0, C. It will go after this transformation, it will go to this point. It's C divided by 2, C divided by 2, and 0. And the other vertices, they actually go to, well, the middle point of the opposite side. So our triangle, it shrinks a little bit, rotates, and its center stays at the same place. So we get homothetic transformation with, let's say, ratio equal to minus 1/2. So it shrinks and rotates. And its center, well, it's the centroid of the triangle. So it has coordinates, excuse me, C over 3, C over 3, and C over 3. So the next step of the solution would be to say the following. So imagine that there is some point on this triangle. This point corresponds to a current situation on our table. So the Polish is somehow spread. And then after this homothetic transformation, this point will go, let's see, I guess here. I'll do it with another color. And then after the next transformation, this triangle shrinks again. Oops, I'm sorry, but yeah, I think you get the picture. So all the points, they move towards the center of our triangle. So after some amount of moves, we will get to the point where all our states are here in the small disk at the center of triangle, where every point differs from another no more than 1%. So we get the required statement of our problem. So here's a little example. I think it's rather beautiful. Do you have any questions at this point? Okay, I hope everything was clear. You can read again the solution in a project file. And yeah, it's easy to prove that this transformation is a homothetic transformation. So try to do it formally by yourself. The next thing I want to talk about is, well, this phase space. You get a set of points as a phase space. And sometimes it is better to consider it not just a set of some points, but add some additional structure. Let's talk about that. Additional structure. So at our example, we actually had a fine structure. Probably some of you know what that is, but if not, don't worry. Well, affine structure just means that we have some type of geometry on a phase space. So we have lines and planes and so forth. So actually this additional structure on a phase space helped us to solve problem number 0. Uh, the next concept is also should be familiar to you because I'm sure you've already used it in some Olympiad problems, uh, graphs. Yeah. So suppose you have some finite amount of points in your set space. We call these points vertices, and when imagine we have edges, maybe oriented, maybe not, if we can move from one point, so from one state to another, both way. But anyway, you get a graph. And sometimes it also can help you to solve the problem. We have such problems uh, in a problems list. Um, the next idea is having some kind of area or volume. So area for two-dimensional spaces, volume for three-dimensional spaces and above. So suppose you have your phase space as a set of points, and you defined a measure, some kind of measure to, well, measure an area of its subsets. It will be crucial for solving problems on probability. So as you can see, there is a first section, geometric probability, and it converts the problem of finding probability of some event uh, to finding just an area or a volume for some subset on a plane or in a space, depending on the problem. And well, the fourth very important structure, type of structure, is topological structure. And actually, well, topological structure. Actually, we don't have such problems in part 1, problems before the semifinal, uh, but there will be problems requiring the use of topological structures in part 2, problems after the semifinal. So I guess we'll talk about it in more details a bit later. And well, one more note on structures. There is a concept in physics, I'm sure in your physics class you all learned it. So suppose we have a point, a particle with its coordinates. And if you just consider some number of particles in space or on the plane, its phase space consists of its coordinates, but let's add a vector v. V stands for velocity. So sometimes it is very important to consider a phase space consisting of coordinates of points and its velocities. So it comes from physics when I have particles moving and colliding. And we have such problems in our part 1, you'll see. And let's talk a little bit about how our project is organized. So part 1, problems before the semifinals. There is a lot of examples of phase spaces. Most of them, well, they're quite simple, but some of them require maybe clever Olympiad style tricks. So part 1, problems before the semifinal. And in part 2, forgot how to write semifinal. Okay, I guess it's this way. And in part 2, we have a couple of problems, but they are huge. They divided into sub-problems, and I warn you, they will require some use of topological structures, but you don't need some prerequisites knowledge to solve them. I guess, as my colleague said, the lesser you know, the better. Yes, you can ask questions about a project in Mattermost. There is a public channel of our project, and also via email. It's all in a projects channel in Mattermost. So please feel free to ask any questions if you don't get something in our problem statements. And also one more note about solving problems. Please try to send us your solutions as soon as you find them, as you solve the problems. Don't wait until the last minute, until the deadline. So as you may see, there is a lot of problems. So try not to send everything at the last second before the semifinal. Otherwise, it would be hard to check all your solutions. So yeah, here we go. That's a project about phase spaces, and please feel free to ask any questions if needed. So maybe, well, did I forget something? Maybe my colleagues will remind me. But I guess that's it for now.
Что, дополнение?